Welcome to week 5. This is CS 480 and 680, Introduction to Machine Learning, as taught at the University of Waterloo in fall 2024. So this is lecture 7, and today we're going to be continuing on our discussion of support vector machines, and specifically looking at the soft margin classifier. This is a generalization of what we covered last time in the maximum margin classifier or optimal separating hyperplane, hard margin classifier. Those things all mean the same thing. Yeah, so quick recap on what we were doing last time. So we were interested in finding the optimal separating hyperplane between two linearly separable classes. So the picture you might have in your head is we've got some scatter points in the top right, and some more data points scattered in the bottom left. And we wanted to draw a separating hyperplane that perfectly separated these two classes, but also and imposed some margin between them. And this, our objective involved minimizing the norm of the weights, or specifically the half squared norm of the weights, subject to the constraints that all points were classified correctly with some margin. And so we solved this by deriving the dual, which yielded the result that the parameter vector and the weight specifically is a weighted sum of the support factors, specifically those that were on the margin. So for this particular data set, these points that are bolded or deeper in color, that these are our support factors. They lie exactly on the margin, and it's a linear combination of these that determine the optimal separating hyperplane. Yeah, so the optimal separating hyperplane perfectly classified everything. There was nothing inside of this margin. But we know that real world data doesn't tend to work like that. And in the first assignment of this course, you were working with the iris data set, for which the Setosa class in the purple here in the upper left, this was linearly separable from the other two classes, Versicolor and Virginica. But Virginica and Versicolor have significant overlap. You can see that they're intermingled with one another. There's some samples of Versicolor way out here, and then there's some samples of Virginica that are way down here. So there's no line, no separating hyperplane that we could draw that would perfectly classify these two samples in these two classes. Similarly, the scatter plot on the right here shows features extracted from images of handwritten digits. This specifically the MNIST data set. And even digits as different as a 1 or a 7, we can see that there's a fuzzy line between those two. There's quite a few 1s that look a bit like 7s, and quite a few 7s that look a bit like 1s. And so there's no decision boundary that we could draw that would always perfectly predict between these two classes. And so, yeah, a lot of real world data, there tends to be a fuzzy line between one class and another. The features tend to overlap a little bit. And so today we're going to be focusing on how to solve that harder problem, specifically when there is some overlap between the classes. So we're moving from this very simpler idealized case that we could solve with the perception or the perceptron or the hard margin SVM, and we're moving to the overlapping case. So the data that we'll see today will look a lot more like this. And our goal is to try to fit a line that does a good job of cutting through the data, but won't get it perfectly right. So be focusing on 3 key questions today. The first, we're going to look at seeing if we can relax the constraints that we had in the hard margin SVM problem to see if we can find a classifier that does a reasonable job, but it won't be perfect because perfect is impossible now in the types of data that we're working with. Um, Second, we're going to be deriving the Lagrangian dual yet again today. We're gonna see if that can lead to any insights into the problem, any deeper understanding as it did when we looked at the hard margin problem. And then last, we'll be thinking about how do we actually go about optimizing this problem and finding the optimal parameters. Yeah, so how can we relax those constraints that we had in margin SVM? So as I said, the hard margin SVM problem concerns maximizing the margin. This is analogous to minimizing the norm of the weights to find a separating hyperplane that correctly classifies all training points, but with a margin of at least one. But the big problem is that if the data is not linearly separable, there's no feasible solution that satisfies this constraint for all points. So to deal with overlapping classes, we're going to do something called a soft margin SVM. So this is going to allow for misclassification or margin violations. So we no longer require everything to be perfectly classified with some margin. And so instead, we're going to, yes, we're not going to have any constraints anymore, like in the hard margin. We're going to introduce a penalty term. That's this guy here. So this is going to count the extent to which each point falls on the wrong side of the margin or is misclassified. And it's going to do this through a max function. And so it does this. So we've got the linear predictor here. So if the linear predictor is less than 1, then this whole term is going to be positive, and then we'll contribute to the penalty. We'll contribute to the penalty, contribute a positive penalty to the objective. Because we want to minimize this problem, then we're penalizing the objective. If, on the other hand, this linear predictor is greater than 1, then this whole term is going to be positive, is going to be negative. And then when we apply the max function, this whole thing is going to be 0. So if we're greater than the margin, then we won't be contributing to the penalty. We also now have a hyperparameter C. And this is going to control the trade-off between maximizing the margin and minimizing the classification errors. So this plot on the right here shows how this soft margin SVM works in practice. So this gray region still represents the margin, and the black dashed line is still going to be our separating hyperplane. But now we can see that there's points inside the margin. So these red points over here, they're inside the margin. Blue points over here are inside their margin. But there's also a few points that are on the wrong side of the separating hyperplane. And so these points that are inside here are going to contribute to the penalty in the objective function. So it's going to allow the model to balance between fitting the training data and maintaining a larger margin. Just to sum up, soft margin SVM still seeks to minimize the norm of the weight factor, but it no longer enforces a hard constraint that every point must be classified with a strict margin. And so by incorporating the penalty term, the model is going to tolerate some errors. So the idea is that this is going to make it more flexible and robust. Just a final note. In this plot in particular, the negative class is in the upper right, and the blue class is negative. That's in the upper right, and in the red class, the positive class is in the lower left. And so that's why we have negative weights, because the decision boundary is actually facing this way. Yeah. So now let's zoom in a little bit more on what's going on near the decision boundary inside the margin. So that's that square region we just saw. That's just blown up. And so let's talk a little bit more about each of these points. So This plot here, yeah, shows the behavior of, or some points that are really close to the decision boundary and specifically within the margin that we want to focus on. So we can categorize points into three groups based on their position relative to the decision boundary in the margins. So let's call incorrectly classified points. That's these ones are on the wrong side of the decision boundary because all the red class is down here, and these red ones are above the line. So if the product of the decision label, the true class label, and the linear predictor is less than 0, then we're gonna say that's incorrectly classified. And so these points are the ones that lie on the wrong side of the decision boundary, and they're going to contribute significantly to the penalty. They're going to contribute a significant penalty because the value inside the max function is going to be positive and large. So we can also identify some, I guess, weakly correctly classified points. And these are going to be ones where the product of the true class label and the linear predictor is between 0 and 1. So these points are within the margin, but they're on the correct side of the decision boundary. So they're going to contribute some penalty, but not as much. Finally, points. We'll call these ones strongly correctly classified if the product of the true class label and the linear predictor is equal to or greater than 1. So they're going to lie outside the margin. So they're going to lie outside the margin area, and they're not going to contribute to the loss at all, because says the value inside loss function 0, or the value once we take the max function is 0. And so if the product is greater than 1, then the point is strongly classified and lies really far away from the margin. So yeah, in this lecture, I'll occasionally use the terms strongly, weakly, and incorrectly classified to describe these three cases. Okay, so we've introduced a penalty term for soft margin SVM to handle margin violations as well as misclassifications in the soft margin SVM formulation. But yeah, let's see if we can build some intuition around that. So the specific penalty is called hinge loss. And to simplify our discussion, we'll refer to the output of the decision function, W transpose x plus b. We're going to call that y hat. And this equation at the top here shows the soft margin SVM objective function as we've been seeing. And right now we're going to focus on what's going on here. Yeah, we're going to focus on this second term. This is the penalty for margin violations. And so the graphs down here depicts the behavior of the hinge loss for one data point. So on the y-axis, we have the magnitude of the penalty. So this is c times max of 0 or 1 minus yi y hat. And in this case, I've set c to just be 1. And on the horizontal axis here, this is the magnitude of the linear predictor, so W transpose xi plus b. And so for the negative class, if the linear predictor is negative, we start off in the strongly classified region. So the penalty is 0 here, so no loss is incurred. And then between 0 and -1, or between -1 and 0, we then move into the weakly classified region. So the point's correctly classified, but still incurs some penalty because it lies inside the margin. And then finally, if the linear predictor is greater than 0, it enters the incorrectly classified region because the penalty just continues to increase again. Right. And then on the right-hand side is the hinge loss for a positively labeled sample, and this just mirrors the behavior of the negative case. Here, if the linear predictor is large and negative, we incur a large loss, but if it's large and positive, we incur 0 loss. And so the penalty is called hinge loss because it looks like a door hinge. So it's got this flat region for strong classifications and this linear increase for incorrect classifications. And it's important to note that the hinge loss is not differentiable at the hinge point. So we can't set its partial derivative to zero as we could with, say, linear regression. So we've also got this new hyperparameter C. So let's take a closer look at what it does. So the soft margin SVM objective function I've got shown here again at the top. And C multiplies the sum of hinge losses. So the scaling the penalty associated, essentially scaling the penalty associated with margin violations and misclassifications. The plot on the left visualizes this penalty term for different values of C. So when C is small, like 0.5, the penalty isn't so steep. So we're placing a smaller penalty on misclassification errors. Another way to think about this is that the SVM is going to tolerate more error in favor of a wider margin. As C increases, the slope of the penalty line becomes steeper. So the SVM is going to become more sensitive to errors and is going to enforce a stricter margin. So it's going to make fewer misclassifications acceptable. We can also explore some extreme situations. So if we set C to 0, the penalty term is going to disappear entirely. So this is going to effectively drive the weights to the uninteresting solution where the weight vector is 0 and no meaningful decision boundary is formed. So yeah, this is just a totally trivial model that's going to classify everything as the same class. On the other hand, if we allow C to become very large, and in the limit of C going to infinity, this is going to reduce the soft margin SVM to really behave as the hard margin SVM in the case were if we had linearly separable data. So it's going to impose a strict separation. It's not going to allow any margin violations or misclassifications. So yeah, while increasing C penalizes violations more heavily, it's important to remember that it results in a model that is less flexible. And so overall, the choice of C allows us to control the trade-off between the margin width and the number of margin violations. So it helps us tune the model to a desired level of complexity and robustness. Quick word of caution here. Some of the texts, specifically those that I have referenced on the course homepage, like the Introduction to Statistical Learning, their derivation, they describe the role of C in the opposite way. So it's almost like a budget for penalty violations. And so this perspective suggests that a lower C would mean lower tolerance for violations, which is not how we are thinking about it. So just a word of caution, if you are reading it in that text in particular, it's going to be opposite from what we're covering here. Right, so yeah, let's play around with this hyperparameter C a little bit. So these scatter plots depict the data as well as the solution using the soft margin SVM. So these are the optimal decision boundaries for 3 values, C of 1, C of 2, and then C of 10. And so I drew these samples, generated these data sets from the same parameterized distributions, but I just used different random seeds. Note that all 3 axes, all 3 plots have the same axis limits, so you can directly compare the results. So on the left, with C set to 1, shows several points within the gray margin area. So this is consistent with the soft margin classifiers we expected. If we increase C to 2 in the middle plot, we see fewer points within the margin because a higher C means a stricter enforcement of the margin, lower tolerance for error. And then finally, if we set C to 10, the SVM tries even harder to minimize violations, and it results in a narrower margin and fewer points inside the margin. So this more rigid boundary better separates the classes, but might be too strict. And so yeah, while C is small, the model prioritizes a wider margin over correctly classifying every point. But as C increases, the SVM places more emphasis on minimizing classification errors, reducing the number of margin violations. However, setting C too high can cause the model to behave like a hard margin SVM, and this would make it less robust to new data, and also might cause the optimization process to fail. We can actually draw a parallel between ridge regression and the soft margin SVM. So for ridge regression, recall ridge regression that we covered a few weeks ago. The objective is to minimize the mean squared error of the model predictions. And we combine this with a regularization term that penalizes the norm of the weight factor. And so this regularization term, lambda, so lambda is the hyperparameter times the norm of W. This discourages large coefficients, which helps prevent overfitting by trying to keep the model simpler. And so we can express ridge regression loss as the expectation of the loss, plus the regularization term to show the balance between fitting the data and controlling model complexity. So let's now compare this to the soft margin SVM. I've changed the order of the terms in the SVM objective to highlight this similarity. And so if we take the loss function to be the hinge loss, the soft margin SVM can be rewritten as the expected hinge loss plus the regularization term. So specifically, we can divide this whole part through by C and the number of samples n to obtain a regularization term inversely proportional to n and C. And yeah, we're allowed to do this because dividing the objective by these scalars doesn't change the position of the minimum or the optimum. So the solution we would find remains unaffected. We're not changing the position of the solution, or yeah. So you can see that now we have a loss part in both ridge regression and soft SVM, and then we have we're adding a penalty proportional to the squared norm of the weights. In ridge regression, we have a hyperparameter lambda, and then in soft SVM, our hyperparameter C. So while ridge regression focuses on minimizing the squared error for regression problems, and soft margin SVM controls classification errors and margin violations through hinge loss, they have a similar structure for regularization to avoid overfitting and achieve better generalization and robustness. So let's bring this idea of regularization back to hyperparameter C. And so as we said, when C is very large, we effectively eliminate this regularization and we recover the maximum or hard margin classifier from last week. So that the weights can get very large and sensitive to training data. And so yeah, here we've got some data sets that were trained with on specifically the hard margin SVM. And what I'm going to show is that even if a separating hyperplane exists for linearly separable data, as it is in this case, I'm going to show you that it might still be beneficial to use a soft margin SVM. So these three plots here show the maximum margin classifiers applied to the same data set, but with different random seeds. Seed of 1, seed of 8, and seed of 42. And so even the data remains linearly separable in all three cases. You can see that the position and the orientation of the separating hyperplane, it changes quite a bit, but from seed to seed. So this variability is because the maximum margin classifier is highly sensitive to small changes in data, particularly to individual observations that fall near the margin. And so the sensitivity can result in different decision boundaries, and this might not generalize well to new data. So yeah, the key point is that even if even if the data are linearly separable, a classifier based on the optimal separating hyperplane, the hard margin hyperplane, might not be desirable because it can be heavily influenced by just a few data points. So this can lead to overfitting. So we're really sensitive to minor variations in the data. And so by allowing for some misclassification using a soft margin SVM, we can actually achieve greater robustness to individual observations and improve classification performance for most of the training observations. So we can also compare the hinge loss to other loss functions that are commonly used in machine learning, as well as those that we've seen in this course so far. The Elements of Statistical Learning text provides a neat discussion of this. So the graph on the left plots these different loss functions, where the x-axis is the output of the linear predictor. They call this YF, and the y-axis shows the corresponding loss. So the hinge loss that we're talking about today is shown in red. This is the one we're using for the soft margin SVM. Gives zero loss, zero penalty for points that are correctly classified with a margin greater than 1, and a linear penalty for points on points inside the margin or on the wrong side of the hyperplane. It continues to increase linearly as we move away from the margin in the wrong direction. Binomial deviance, which is shown in green, this is what we've been calling this cross entropy loss. So this is the negative log likelihood loss used in logistic regression. So it behaves similarly to the hinge loss for points that are far from the margin and incorrectly classified. And then also for points that are far from the margin and correctly classified. Gives a zero penalty for strongly classified points, and it approaches a linear penalty for points on the wrong side of the margin. The squared error loss used in regression is shown in orange. He penalizes both positive and negative errors quadratically. And then there's also something called the Huber loss, which is shown in blue, which aims to provide a smooth transition between the squared error and hinge loss. But yeah, we haven't encountered this yet. We're not going to be dealing with that today. Okay, so we understand the problem. We've talked about the SVM objective function. We've talked about the importance of of tolerating some error in favor of being able to generalize to new situations and slightly new data sets. But now we're going to see, how is this actually solved, and can we gain any insights by deriving the dual formulation of the objective as we did for the hard margin SVM. So an important thing to note is that we could technically optimize the primal form of soft SVM using numerical methods like gradient descent. So yeah, if we look at the soft margin SVM formulation at the top, we can see that it's structured as a regularization problem with a linear loss. And so this means that in principle, we could implement a gradient descent-based optimization strategy, specifically a stochastic gradient descent optimization strategy to find the solution. But when we derived the dual form of the hard margin SVM problem last week, which I've got here, we gained substantial insights that went beyond simply finding the optimal weights. Specifically, the dual form allowed us to view the problem geometrically. It provided some insights into which data points influence the decision boundary, specifically the support vectors that I've marked off here. Yeah, so these ones on the margin. We found out that they're the only ones we need to compute the decision boundary, to compute the parameter vector, and then the others, all other training data had no effect whatsoever. So after training, we could just throw all this away and only keep our support vectors around. And because that's all we needed in order to calculate the weights. So yeah, while we could move forward with optimizing the primal objective of soft margin SVM, deriving the dual form is going to enrich our understanding of the problem. But yeah, just a warning. Deriving the dual is going to make this problem more complicated at first, but I assure you that the insights are going to absolutely be worth it. In particular, when we covered linear regression a few weeks ago, we started talking about regularization, and I think this might help satisfy some of the nagging questions that you've had in the back of your mind. Okay, so how are we going to do this? So what we're going to do to make the transition from the soft margin SVM problem into its dual form, we're going to introduce something called slack variables. And so these are denoted by by this squiggly term here. These slack variables are going to quantify how much each point violates the margin. And so in the soft margin SVM problem, sorry. So in the soft margin SVM objective shown at the top, the hinge loss, when it's the max of 0 and 1 minus the product of the true class label and the linear predictor y hat. This is going to tell us how far each point is from being correctly classified with a margin of at least 1. But this doesn't directly provide a way to measure individual violations. And so this is where the slack variables are going to come in, and we're going to have one for each data set. And so what do I mean by this? So let's consider one of these points near the soft SVM boundary. So we're going to say if the slack variable xi, that's how you pronounce this, xi, is equal to 0, then the point is correctly classified with a margin of at least 1, and is going to lie on the correct side of both the hyperplane and the margin. If xi is greater than 0 but less than 1, like this point here, the point is correctly classified but lies within the margin area. So it's violated the margin, but is still on the correct side of the hyperplane. Finally, if xi is greater than 1, then the point is on the wrong side of the decision boundary and is misclassified. And so in the plot, these points lie outside the margin, showing that they've been classified incorrectly. Okay, so the idea is that the slack variables xi measures the distance of a weakly or misclassified point from the margin. So it measures the distance from a weakly or misclassified point from the margin. So if that's the case, then 1 minus xi gives us the position relative to the decision boundary. So this is shown for this blue point in the bottom right here. And so why is that the case? Because we know that this is y of negative. We know that this is 1 here. And then this is going to be 1 minus our slack variable. So this is the slack variable here. And then this is going to be 1 minus the slack variable. So right, so this is 1. Our slack variable would be this distance here. And then this is 1 minus the slack variable. Okay, and so so these are our slack variables. And then we introduce a constraint, a set of constraints that the linear predictor associated with each point, adjusted by the true class label, is no less than this amount, 1 minus xi. And also, in order for this to be meaningful, that slack variables are non-negative. So yeah, I completely acknowledge that this seems overly complicated because we took an unconstrained problem that we could optimize, and then made it constrained. But the idea is that introducing these slack variables are going to formalize the concept of margin variables. And the point is that we'll be able to derive the dual formulation of the problem, which we could then optimize in another way, but also get some insight into the problem. Okay, so we require that the product of the class label and the linear predictor y hat have to be at least 1 minus the corresponding slack variable xi for each point, and that all slack variables are non-negative. Okay, so now we're ready to take the next step in deriving the dual form of the soft margin SVM by incorporating these constraints using Lagrange multipliers like we did last class. So to move from the primal optimization problem to the dual form, we introduced this set of Lagrange multipliers to handle the constraints on the slack variables, and as well as the non-negative term. Right, so we to introduce these constraints using Lagrange multipliers to form the Lagrangian. And it's going to allow us to enforce these constraints while keeping the problem in this unconstrained form. Right, so in the Lagrangian now you can see that we have two sets of Lagrange multipliers. We've got lambda sub I, and this is used for constraints involving the slack variables and the margin. And then mu sub I, this is used for the non-negativity constraints on each slack variable. And so the resulting Lagrangian expression includes the original objective function minus the two penalty terms. So that first penalty term is going to involve lambda sub I. This is penalizes the violations on the constraint y times y hat greater than or equal to 1 minus xi. And if the product y hat is less than 1 minus xi, then the constraint's violated, and then the term inside the brackets becomes negative. And so this negative value is going to contribute a penalty to the Lagrangian. So it's going to provide a mechanism to push the optimization back towards the feasible region where the constraints are satisfied. And then the second penalty term involving mu sub I, this is going to ensure that the slack variables remain non-negative. So this is going to prevent them from taking on negative values that would make the constraints meaningless. So our ultimate goal is to manipulate the Lagrangian to eliminate the primal variables, which are W, B, and slack variables xi, so that the final expression only involves the dual variables, which is lambda sub I, mu sub I, and any constants. Okay, so let's continue our derivation by expanding the Lagrangian function. So I've got the Lagrangian from the last slide at the top again. So this includes the original objective function, as well as the constraints on the slack variable, and the penalty terms enforced by the Lagrange multipliers. Sorry, this was the penalty term on the slack variables. Right. And so, yeah, just to reiterate, our ultimate goal is to separate out the primal variables and eventually isolate the dual variables lambda and mu. Okay, so let's focus on this third term. We can see that it can be expanded by multiplying lambda I through. So each we can multiply lambda I through each respective terms. So this is going to give us lambda I, yi, and then lambda I times minus 1, minus minus, that's going to cancel. So that should give us plus lambda I. And then lambda I minus xc, that'll be minus, a minus, a minus, so it'll still stay negative. All right, and so after expanding, then we can substitute in the expression for the linear predictor y hat, which is w transpose x plus b. And then we'll be able to sub that in there to get this third line. And so, all right, now we can expand that into these two terms here. Now we've got this final big expression in terms of w and b and lambda and xc, sorry, w, b, xc, lambda, and mu, as well as our training data, xc and yi. So that is 1, 2, 3, 4, 5, 6, 7 variables, and three of those are the number of variables is the number of samples that we have. All right. So next, we can take the partial derivatives of the Lagrangian with respect to the primal variables to enforce the stationarity condition to try and eliminate the primal variables from the Lagrangian. So first, we'll take the derivative of the Lagrangian with respect to the weight vector w. So we can see that only the first two terms matter here. So this is going to leave us with w minus the sum over lambda I yi xi. And then setting this derivative to 0 shows that w can be represented entirely in terms of the dual variables lambda sub I, the class labels yi, and the training data, and the feature vectors x sub I. So yeah, this relationship tells us that in order to solve the problem, we have to express the weight vector as a weighted sum of the data points, where each point's weight is determined by its corresponding lambda sub I value. So this constraint is also what we saw in the hard margin SVM, which told us that the parameter vector is expressed as a linear combination of the training data points. So next, let's differentiate the Lagrangian with respect to the bias term b. And so only the third term is relevant here. And so setting this derivative to 0 leads to the constraint that the sum of lambda sub I times y sub I over all data points must be 0. This is also what we saw in the hard margin SVM. Essentially, it ensures that the decision boundary is correctly balanced between the two classes and that the constraints are satisfied across the entire data set. And so finally, let's take the derivative of the Lagrangian with respect to each slack variable, or specifically, one slack variable. And so for this, we only need to consider the last three terms, where we see sums of c scaled by c, lambda I, and mu I, respectively. So the partial derivative is c minus lambda I minus mu I. And so setting this equal to 0 then gives us a direct relationship between the Lagrange multipliers lambda I and mu I through c. Specifically, that mu I is equal to c minus lambda I. Okay, so now we can move on to enforcing these stationarity conditions. So again, I've got the full Lagrangian up top, and the conditions we just derived are color-coded to make this part easier to follow. So let's go ahead and substitute the expression for w back into the Lagrangian. So it's shown in teal here. And so if we do that, it's gonna result in two terms of quadratic forms that involve lambda I, lambda j, the class labels yi, yj, and xi, xj, and the inner product of feature vectors xi and xj. So we also have something similar going on here. And it turns out that both of these two terms can be expanded, it can be simplified into double summations. And so we can then apply the stationarity condition that we derive with respect to the bias term B, shown in orange. Um, and so, yeah, since we've identified that the sum of Lagrange multipliers times the training or the class labels must be zero, we can eliminate this term involving bias, because we know that this one's going to have to be zero. And so now let's minimize the Lagrangian with respect to the slack variables C. And so the relationship that mu I equals C minus lambda I, we can substitute for mu I into the Lagrangian. And so I guess first we could rewrite this expression here because we see sums over C 3 times. So we can rewrite this into a simpler form here. And then let's plug in this condition that we derived in the last step for mu I. And then we're going to get C minus lambda I minus C minus lambda I. And so this is going to go to 0. And so we just eliminate that completely from the equation. And so now we can add these two terms together, and that's going to leave us with an expression that depends solely on the dual variables, lambda sub I, as well as the training data. So it might, be a good point to pause the video at this point to consider whether you've seen this anywhere before. Yeah. If you hopefully you recognize that that objective, because we have found the exact same dual objective as we did for the hard margin SVM problem. This isn't a mistake. This is real. And when I first saw this, I remember being extremely frustrated. Like, what was the point of all that work? You've got to be kidding me. This is actually a pretty interesting result on its own. So what this means is that the dual Lagrangian doesn't depend on whether the constraints included slack variables. So the function that we're trying to maximize is identical for the soft and hard margin problems, at least from the dual perspective. But they have to give different answers, right? So what's going on? And so we have forgotten about the constraints a little bit. And so to see the differences, we have to take those into account and take a closer look at the constraints on the dual variables. And so recall that for the hard margin SVM, we had the constraint that the sum of the product of class labels and multipliers must be 0, essentially enforcing that balance between a weighted sum of points on either side of the decision boundary, and also that the multipliers are non-negative. And so we have these constraints on the soft SVM dual as well. But we also had 2 more that concern the non-negativity constraint on the slack variables, mu I, that the mu i's that we eliminated from the objective after satisfying one of the stationarity conditions, and one that locks the dual variables into a one-to-one relationship through C. But these mu's, they don't even show up in the objective anymore. So what does that mean for the lambdas that are actually there? So we can combine these last 2 constraints, which tell us that the difference between C and lambda is non-negative. So if mu I is equal to C minus lambda I, then we can take this here and plug it in up here, and then C minus lambda I is going to have to be non-negative. But in order for this to be true, lambda must be at most C. And so combining this with the non-negativity constraint on lambda, we can find that lambda is both lower and upper bounded in the soft margin SVM. So putting this all together, we can see that whereas the hard margin, the lambdas were constrained solely from below, specifically that they have to be non-negative. In soft margin SVM, there's also an they're also upper bounded by hyperparameter C. And so this is surprising because even though the hard margin SVM can be thought of as more constrained than the soft margin in the primal formulation, the soft margin SVM is actually more constrained in the dual in a purely, at least in a purely mathematical sense on the Lagrangian multipliers. So the feasible region of the dual is different than that of the dual for the hard margin SVM. And so while this might make the feasible region smaller compared to the hard margin SVM, it seems to introduce more flexibility in the model, allowing it to handle non-separable data and misclassifications that the hard margin SVM just can't tolerate at all. So what does this mean for what we're trying to optimize? So for that, we can again consider the complementary slackness condition. The complementary slackness condition here tells us that for each data point, either its Lagrange multiplier denoted as lambda is 0, or the constraint that involves the class label, the decision boundary, and the slack variable is exactly 0. So let's consider these two cases separately. If lambda I is 0, the points doesn't influence the decision boundary. And we know that for this to be true, the other term must be greater than 0. And specifically that the product of the class label and the linear predictor must be greater than 1. And so these points are correctly classified, that they lie outside the margin. These aren't going to be included in the computation of the weight factor. When lambda is non-zero, though, it indicates that the point lies on the margin or violates it. And so and then when the slack variable C is 0, the point is exactly on the margin. And then where C is greater than 0, these are points that are misclassified So the decision boundary is determined by points that are exactly on the margin or within the margin. Okay, so that helps give us a geometric picture of what's going on. But we also know a bit more about the Lagrangian multipliers that determine the influence of a single training point on the decision boundary. Specifically, lambda is constrained to be less than or equal to C. So the hyperparameter C limits how large alpha could be. So it in turn places an upper bound on how much influence any one support factor can have. And so if C is set to a high value, it allows lambda values to become larger. So any one point could have a large influence on the results. So from the primal perspective, the SVM would penalize classification errors more strictly with a high C. So this would lead to a narrower margin and potentially overfitting to the training data. So we can see now a direct relationship between the size of the weights and the width of the margin. Conversely, if like a smaller value of C would constrain lambda to smaller values. And so the parameter vector would tend to be smaller. From the primal perspective, we'd be placing a smaller penalization on misclassification errors. And so we'd be encouraging a larger margin, which could lead to better generalization on unseen data. All right. And so yeah, how do we optimize how do we optimize this the dual form? So uh, yeah, it's remarkably similar to how to solve it for the hard margin problem. We can still use your favorite convex optimization package. I've been continuing on with CVXPy. I've had quite a bit of luck with that. Um, but yeah, the variables would be your lambdas. For the objective, you would that's what you would plug in there. And the only difference would be now you have uh, an upper and a lower bound on lambda. So you'd have three constraints if you include this one. So yeah, lambda would have to be non-negative, and lambda would have to is upper bounded by C. So really similar. And so yeah, once you solve that problem, then you can start playing around with C. And so yeah, just before we close out the talk, I'd like to show you a little bit what that looks like. So let's start off with C at a fairly high value. We can see that there's a fairly narrow margin that ended up getting found. There's not that many points um, inside the margin. Um, and we can also see that, so yeah, crucially, this is the same generating distribution, the data points are being drawn from the same distribution, just with different initial random seeds. And so that if that's the only thing that's different between each of these three plots, then you can see that the weight vector or the parameter vector moves around quite a bit. We'd see the orientation changing, the width changes a little bit. Um, and yeah, it's even though just slightly different training data, we're getting very different separating hyperplanes. And then if we shrink C down a little bit more, we can see like immediately the margin grew quite a lot. So we've got a wider margin. Um, but now, uh, so there's more points inside the margin. But then also the weights got a bit smaller. So they were, around okay, 7, 5, 4, and now they're close to 3. And there's very little variation from parameter vector to parameter vector. So there's lower variance from training set to training set. And let's shrink C down even more. We've got, yeah, the weights shrunk even more, and the margin expanded even more. So we're seeing this effect, um, of putting a cap on the Lagrange multipliers in the dual problem, in terms of uh, we're not allowing any one training point to have a huge influence on the weight factor. Instead, the limit of any one any one support vector is capped to a lower amount. Uh, right. So we talked about one way to optimize this problem, which was deriving the dual and then solving it as a convex optimization problem. But I did mention that there is a way to solve this using a stochastic gradient descent method. So specifically using SGD on the primal objective. And so it'd be a good idea to pause the video at this point to see if you can try to derive the stochastic gradient descent update on the primal objective. All right, did you have any luck? Okay. So I would imagine that one problem you might have run into is, how do you derive how do you take the derivative of a max function, right? It's not differentiable at the point where it's actually 0. Okay, so what you can do instead is split the SGD update into two cases. So one where yi hat is less than one, so that the term inside the max function is positive, and then one for everything else. And so you just sidestep that. You sidestep the fact that you can't take the derivative when the derivative is discontinuous isn't continuous. And so if you do that, then the gradient with respect to w, in the case where yi hat is less than one, making this whole term positive, then we would see that okay, this first term, the two would come down, cancel out the half, and then we'd have w, and then we line c times the gradient with respect, or that then we want the gradient with respect to yi w xi. So that would give us c yi xi, and so minus c yi xi. So that's the gradient with respect to w in the case of yi being negative. And then if it's positive or anything else, then the gradient is just the weights. So yeah, it's kind of interesting. We're always in the gradient descent update or the SGD update, we would always be subtracting the weights a little bit. And then with the gradient with respect to the bias, we could do something similar. Then we'd have C minus yi, yeah, C minus yi, and that's our gradient update. But then it would be zero otherwise. All right. So that brings us to the end of our lecture. And yeah, just to summarize, so I talked about the hinge loss in the SVM problem. So you should be able to recognize that, as well as describe some of its properties, distinguish it from other losses that we've encountered. Also, talk about the geometric properties of the soft SVM decision boundary. So we talked about the margin, what the support vectors are now. They're a little bit different than in the hard margin SVM. We have slack variables to quantify the distance between a training point and the margin. We talked a lot about the effect of hyperparameter C on model performance, generalization, the norm of the weights. We looked at it empirically, we looked at it analytically, we looked at it from the primal perspective, from the dual perspective. So we've got lots of ways to think about the effect of the hyperparameter C on model performance. And we can also combine this new knowledge with concepts that we've encountered before, such as using cross-validation to select that hyperparameter for us. And we also encountered two different algorithms to solve the soft SVM problem. Because we didn't talk about explicitly the strengths and limitations of each of these two algorithms. But I think that, yeah, that's a good exercise for you to think on your own. When would it make sense to solve the dual directly? When would it make sense instead to use stochastic gradient descent on the primal? All right, so thanks for your attention, everyone. We'll see you back here next time when we start in on kernel method.